Welcome to Calculus. Today we will investigate Newton's method of approximating zeros of functions. We'll take a look at one example of the function f of x equals negative x cubed plus x squared plus 1. So what we're provided with is a guess about the real zero for this polynomial function. The guess is that the zero is 1.2. And the guess here is provided. You could come up with a guess that's valid by using the intermediate value theorem. But we have a guess, and what we want to do is use 3 iterations of Newton's method to closer and closer approximate the real zero or zeros of the function. So let's give the rule that we would use to perform Newton's method. This is a way that uses linear approximations or tangent lines to work from one approximation to the next. So it's a recursive method in order to get closer and closer and closer to a zero that may be real, but it may be irrational. So it comes out of a time before calculators when such a method really would have been very useful if you had a function you were trying to find where it's crossing the x-axis, but it wasn't rational number. So let's start off with the rule. It comes again from the linearization of a function. So the way that it appears it's useful for us here with Newton's method is that if I have some term C1, which is going to be equivalent to our guess here of 1.2, the next approximation, C2, would be equal to that first approximation or guess minus this quotient. So the quotient is the value of the function at that C1 domain value divided by the value of the derivative of the function at that same C value. So let's run through 3 iterations of this method to see how close we can get to the real zero of this polynomial function. So I do need to define something before I go, and that's the derivative of f of x. I have f of x itself here. I'll highlight it in the blue. And we'll be using that extensively in that numerator of the quotient, but we need the denominator, the derivative. So we can write that pretty easily. The derivative of f of x is going to be negative 3 x squared plus 2x. And really, those are the 2 things that I need from the function to perform Newton's method. I'll highlight that as well just to emphasize these kind of are the basic building blocks for using that recursive method. So let's set it up. And the way we'll do it is we'll write the first one here, and then we'll go over to the calculator to calculate it since it's got a lot of decimals. And then we'll come back here to do the second and the third iterations. So I'm going to start off by substituting some values in. So C2 is going to be equal to the initial guess 1.2 minus, so I'm going to put the function, the original function, negative, then I'm substituting in 1.24x, so negative 1.2 cubed plus 1.2 squared plus 1, so that's the value of the function at 1.2 over negative 3 times 1.2 squared plus 2 times 1.2. So that's the value of the derivative at 1.2. So I need to calculate that, and I just want to get a decimal approximation for C sub 2. This will be our first iteration. So let's go over to the calculator. And all I need to do is input this in and get a decimal approximation. So we'll just type the way we wrote 1.2 minus, in the numerator, negative 1.2 cubed plus 1.2 squared plus 1 over negative 3 times 1.2 squared plus 2 times 1.2. And our value there is 1.5708333. It keeps going. So what I want to do is I want to take this in the first 7 decimal places. So we'll go to 333. So again, let's go back to our notes screen so that we can set up the second iteration. And we'll record that down there. So again, that value that we had just approximated was 1.5708333. So when I go to set up the second iteration, now what I'm looking to find is really C sub 3. So that's going to be the previous term. So here we can clearly see how it's recursive. It's going to be 1.5708333 minus, and what's the same as the function, what's changing is the specific x value. So this is negative 1.5708333 cubed plus 1.5708333 squared plus 1. And then in the denominator, the value of the derivative at 1.5708333. So that first term is squared plus 2 times 1.5708333. As you can see, a lot of the work there is just juggling long approximations of decimals. So again, this is my second iteration. I'm looking to see something that's closer and closer and closer to the 0. So let's switch over to our calculator again to calculate that. So we'll start off with that C sub 2 subtracted by negative parentheses 1.57 cubed plus 1.57 squared plus 1, all over the value of the derivative, negative 3 times 1.57 squared plus 2 times 1.57. So again, we're using that iteration. It gives me another approximation. So it's gone down by about a tenth, 1.474951. I'll round that to 6. So again, I've got that approximation. Now I want to run it for a third iteration again, and then at that point we can check the actual function since we have access to a graphing calculator. But we'll head back to our note screen to set it up for the final iteration here. So first of all, we'll just write what that approximate value is. So C sub 3 had about the value of 1.47495516. So now we're ready to calculate the last iteration. So this is going to be for us C4, C sub 4. And it's going to be equal to C sub 3's value, so 1.47495516. Minus, so again, it's the same function, it's just the x value that's changing, and I'm using the previous approximation with each subsequent approximation. And again, a lot of the work is just writing that decimal repeatedly. So there's the value of the derivative there. Squared plus 2 times the same value, 1.47495516. And this will be our final iteration. And then at that point, we want to graph the function and see whereabouts are we in terms of locating the actual 0. So one last time to the calculator. So we'll type this in for the first value. So 1.474951, we'll round to 6. So we start with the previous approximation, And then we're going to make our fraction here. So the value of the function at that value cubed plus the previous approximation 1.47 squared plus 1. And that's all over -3 times that approximation squared. This is the value of the derivative plus 2 times the value of the previous approximation. And that gives me this third iteration of 1.46565. We could round to 3. So I'll record that down. That's our third iteration. That's the estimate of the value of the function after we've done this process 3 times. So it should be getting better and better and better. I notice that the values are decreasing, but they start to decrease less as we make further iterations. So let's graph the function. So the function itself was f of x equals -x cubed plus x squared plus 1. And just by inspection of the graph, I can see that it has 1, 0 there. It's here between 1 and 2. So let's get a table because that's how we want to graph this function. And looks like the domain -2 through 2 is a good slice of the function. So -2 is at 13, -1 is at 3. Y-intercept is 1. We've got a point at 1, 1, and then at 2, -3. So I'll record that table. I don't see that I've got a 0 recorded here, but according to intermediate value theorem, there should be one between 1 and 2 because I see a change in sign between the outputs, the y values of 1 and the y value of 2. It goes from positive to negative. And I can see it here on the graph. So the nice thing about this graphing calculator is I can just click. And so what I'm seeing is the calculated approximation for that 0 is 1.466. And when I compare that with my third iteration, I see that if I rounded that to the nearest thousandth, they would be identical. So the method really does work as a way of narrowing down your guesses towards something that's very close to the actual irrational 0. So let's finalize our answer by heading back to the notes and graphing this function. So I'll just put the table that we had recorded right in this space here. So it's x, and we'd use -2, -1, 0, 1, and 2. And our y values, or f of x values, were 13, 3, 1, 1, and -3. So let's graph here. I can't really graph -2, 13 unless I want to start counting 9, 10, 11, 12, 13. So it's very high up in the equation. We'll place it there. -1 is at 3. That I can graph. 0 is 1, 1, 1, and then 2, -3. And we'll place our graph. So it descends on the left. Let's see if we can make that more steady. Hits a minimum between 0 and 1, goes up, and then goes back down. And the 0 that we approximated, let's go ahead and record that here. So C sub 4, we had found the approximation 1.465655.3, and that was awfully close to the value that was actually given by the calculator for the x-intercept. So thank you for joining for this investigation of Newton's method for approximating zeros. I'll let you approximate your own zeros. See you soon.